Welcome back to the studio. This is the third video in the 14th chapter of the Crystal Clear Electronics video series. In this part, we will be demonstrating a specific type of diode.
A Zener diode is very similar to the diode you have already learned about. You can see its voltage current curve and schematic symbol in the picture. At first glance, there isn't any difference between the voltage current curve of a Zener diode and a regular diode. However, there are two important differences in the reverse biased region near the breakdown range. The breakdown voltage of a given Zener diode is known more accurately than that of an ordinary diode, and we call it the Zener voltage. On the other hand, the curve is very steep in the breakdown region compared to a regular diode. This means that when the reverse current changes, the reverse voltage on the diode will stay very close to the Zener voltage and not deviate very much. This characteristic of the device makes it very useful wherever we need a constant voltage over a range of different currents. It is important that we connect Zener diodes backwards compared to regular diodes, so their cathode will be on a more positive potential compared to the anode, since this is how the Zener voltage drops. Zener diodes are often used as simple voltage stabilizers. They can be found in a wide variety of through-hole mounted and surface mounted forms. Generally, the marking of the terminals follows the standard diode marking, with the side marked with a line being the cathode. In the circuit, the Zener diode has a Zener voltage of 5.1 volts. If the voltage Vz exceeds this, the Zener diode will go into breakdown and current will start to flow, keeping Vz at a constant 5.1 volts. This also means that a higher voltage than 5.1 volts cannot appear on the Vz output regardless of the input Vs voltage. Below 5.1 volts, the Zener diode stays turned off and doesn't conduct. As no current is flowing through the diode, the input and output voltages are the same. You can find out more about Zener diodes in the 20th chapter. For now, we just wanted to introduce its basic features. Our next circuit can be used to test 12-volt batteries. It uses two Zener diodes to shift the voltage level of a transistor circuit. We have connected two 3-volt Zener diodes in series to the emitter of the transistor to increase the emitter voltage to 6 volts.
Ahhoz, hogy a Zener diódákon kialakuljon a 3 voltos Zener feszültség, pár milliampernyi áramot kell rajtuk átfolyatni.
A small current is needed for the Zener diodes to hold their rated voltage, which is provided through R4 from the power supply. Why is shifting the voltage beneficial? The transistor will turn on if the voltage between the base and the emitter is greater than 0.6 volts. Since between the emitter and the ground there are two Zener diodes with voltages UZ1 and UZ2, the voltage needed at the base for the transistor to turn on is 3 volts plus 3 volts plus 0.6 volts, that is 6.6 volts. The base of the transistor is connected to a voltage divider formed by R1 and R2. Because the values of these two resistors are the same, the voltage at the base of the transistor will be half the supply voltage when the transistor is off, as there is no base current flowing. Let's see what happens when 13 volts is connected to the input. In this case, the base voltage will be 13 volts divided by 2, which equals 6.5 volts. The transistor needs 6.6 volts to turn on, so it stays turned off and the LED stays off. You need to connect at least 2 times 6.6 volts, that is 13.2 volts to the input for the LED to start lighting up. In practice, because our components are never exactly precise, the LED starts to glow faintly at 12 volts, and at 14 volts it lights up with almost full brightness. This way, the small circuit can be used to test the voltage of 12-volt batteries.
Our parts package contains 3.3 volt Zener diodes, so the calculated values will vary slightly. The theoretical voltage required to open the transistor is 2 times 3.3 volts plus 0.6 volts, which is 7.2 volts, which means that the transistor would open at an input voltage of 14.4 volts.
In practice, the tolerance of the components again affects the operation. At a 12-volt input, the LED is already glowing faintly, and at around 13 volts, it is clearly visible that it is lit.
We will end this practical example. If you are curious how we can compare the amplitude of analog signals, stay tuned for the next part. Bye!
Bye!